You ever look at a massive skyscraper and just wonder, how does something that heavy stand on what's, well, basically just dirt? The secret isn't just in the steel and concrete you see, but in a deep understanding of the ground itself. That secret, it's called soil classification, and it's pretty much what makes our modern world possible.
You know, it's a fundamental truth we kind of forget about. Every road we drive on, every house we live in, every single towering office block, they all rely completely on the soil they're built on, for their stability, for their safety. And when engineers don't fully get what's going on with that ground, the results can be, well, they can be catastrophic. Buildings can lean, foundations crack, whole structures can fail. It's a powerful reminder that nope, not all soil is created equal.
Which, of course, brings us to the big question. How do we avoid disaster? How do engineers know for sure if the ground is strong enough to hold up a bridge or a high-rise? Well, the answer is a systematic process of testing and classifying. It's about giving the soil a name that reveals its true character.
You can almost think of it like a personality test, but for the Earth. Before any construction starts, engineers have to know exactly what they're dealing with. Is the soil sandy and stable, or is it maybe clay-like and going to swell up when it rains? This is exactly where soil classification comes in.
It's a really systematic scientific method. Geotechnical engineers, those are the specialists who study Earth materials. They use a series of pretty simple tests to figure out the type of soil on a site and, way more importantly, predict how it's going to behave under a whole lot of pressure.
Okay, so to simplify this complex world that's right under our feet, engineers start by sorting soils into two big families. It's all based on how their tiny little particles interact with each other.
On one side, you've got your granular soils, think sands and gravels. Their strength comes from friction between all those individual grains, kind of like a pile of tiny, rough rocks locking themselves together. Then on the other side, you have cohesive soils, like clays. Their particles are actually bound together by electrochemical forces, which gives them that sticky, plastic feeling. This is the first major clue from our soils personality test, and it really determines everything that comes next.
All right, so let's dive into that first family, granular soils. How do we test them? Well, for these soils, the single most important thing is the size of the particles. And the tool for that job is the good old-fashioned sieve. And this right here is the key. It's not just about whether it's sand or gravel, but about the mix of different sizes within that sample. This mix, or distribution, is what tells an engineer how the particles will pack together and, ultimately, how strong that soil is going to be.
The process itself, it's called a sieve analysis, and it's actually beautifully simple. Just imagine taking a dried soil sample and pouring it into a stack of sieves, right? Each one has a finer mesh than the one above it. You give it a good shake, and then engineers can just weigh the soil that got caught on each level. It creates this super precise blueprint of its particle sizes. This blueprint has a name. It's called the soil's grading. Now, a well-graded soil, that's one with a good mix of lots of different particle sizes. The smaller bits fill in the gaps between the bigger ones, and that creates a really dense, stable, and strong material. A poorly graded soil, on the other hand, is made up of particles that are all about the same size, which leaves more empty space and makes it a lot less stable.
But what about our second family, the cohesive soils? With things like clays and silts, particle size isn't the whole story. For these, we need a totally different set of tests, and they're focused on something called the Atterberg limits.
For these soils, the game completely changes. Everything, and I mean everything, depends on one critical factor: water content. A little bit of water can make clay strong and workable, but too much can turn it into a useless liquid mess. These crucial tipping points are called the Atterberg limits. They are specific water content percentages that mark the exact boundary where the soil's behavior dramatically changes, from being a brittle solid to a moldable plastic and then to a flowing liquid.
And this transition, it happens in really clear stages. When it's dry, a cohesive soil is in a solid state. It's hard, it'll crumble if you try to shape it. Add a bit of water, and it enters the plastic state. Now you can roll it, you can mold it, just like modeling clay. But add even more water, and it crosses the liquid limit. That's where it can't hold a shape anymore and just starts to flow.
Now, that workable modeling clay phase, that is incredibly important. The range of water content between that plastic limit and the liquid limit is called the plasticity index. It tells engineers how sensitive the soil is to changes in moisture, and it's a huge indicator of its engineering properties.
So, we've got results from our sieve tests for granular soils, and we have Atterberg limit tests for the cohesive ones. How do we turn all this data into a simple, useful tool? Well, the answer is to give this soil a formal name.
Engineers use standardized frameworks, like the British Soil Classification System. These systems are basically the rulebook for combining the main soil type, like sand or gravel, with its secondary characteristics to create a formal, official classification.
So for instance, let's say a sieve analysis shows a soil is mostly made up of sand particles, but it also has a good bit of finer silt in it. In the system, it gets classified as a silty sand. Notice how the main component is in all caps? That makes it super clear at a glance what the dominant characteristic is.
And this brings us right back to our original problem, doesn't it? This whole naming system isn't just some academic exercise. It's the absolute foundation of safe construction.
This quote from the source material just sums it up perfectly. The classification is a powerful kind of shorthand. It lets an engineer look at a name like silty sand and instantly understand a whole range of likely behaviors, potential challenges, and all the design issues they need to think about for their project.
I mean, just think about how much information is packed into that simple name. It can tell an engineer how strong the soil might be, how it'll compress under a heavy load, how easily water will move through it, and even if it's likely to shrink or swell with the seasons. It's a whole profile in just 2 words.
So the next time you see a skyscraper just reaching for the clouds, remember that its journey didn't start with a steel game. It started with a simple handful of earth and the crucial science of knowing exactly what that earth is made of.